All right, working on parent functions today. So with our functions, and you've actually talked about quite a few of them between Algebra 1, and we're going to talk about quite a few more of them going forward through this year. So our functions are simply a family of graphs that display similar characteristics. So what that means is they follow patterns. And that's really the majority of what mathematics is you find the patterns, so you know what you're dealing with, and then you follow a set of rules based on the patterns that you see. So we have different groups, which are referred to as families, of functions that all follow similar characteristics. Their similar characteristics can be found in their equations, they can be found on the graphs, they can be found in the tables, although sometimes that's a little trickier to see because we don't always look at the full table, we always look at a section of the table, but they do exist in there. So what we're going to do is we're going to go through our different families of functions here. We're going to talk about the parent functions in each one and what the characteristics are and what the patterns are essentially. So each family has what we call a parent function, which is the simplest function within that family. That is what we call our parent function. And then what happens with that parent function is we take it and we shift it around and we make some changes to it, and that's the other functions that we end up dealing with. So we're going to start off with the one that you've been dealing with for most of your mathematical careers. Our linear function. So our linear parent function is f of x equals x. So our linear functions follow the pattern that they're always constant. I'll talk about that when we talk about our characteristics. They're always constant, they're always the same. They're not going to change. The average rate of change is always the same, so it's always increasing by the same amount, or it's always decreasing by the same amount. So looking at our graph, our parent function has a slope of 1, and it goes through the origin, and it looks like that. So our parent function for our linear is f of x equals x, which is also y equals x, because remember, f of x and y are interchangeable. So for our linear functions, our domain is going to be everything xer, unless I chop off part of it. Your domain for your linear functions are going to be xer. And our range is going to be yer. Those are always going to be the same. For this parent function, our x-intercept and our y-intercepts are both zeros. Those do change within the function family as we move the graph around the coordinate plane. But for our parent function, they're both at 0, 0. Our linear function will always have only one root. Reason being, the exponent over here on our x is a 1. That exponent always is a hint as to how many roots that you're going to have. And that's something that I'll keep talking about as we go through our different functions. So next is our end behavior. So as x approaches infinity, which is going to be over here on the right side, our parent function is also approaching infinity, meaning that my right side is going up, it's increasing. It will always be increasing for our linear function. It's not going to all of a sudden curve and go down. And then our left side, so as x approaches negative infinity, so that's our left side over here. Our graph, as you can see, is going down also to negative infinity. And remember, we talked about in the last set of notes how these are our new notations for our end behaviors. This graph is a continuous graph. There's no breaks or jumps in it. And this is an odd symmetry function. If I were to flip my paper upside down, this would demonstrate odd symmetry there. So those are our linear functions. Been dealing with those since middle school. Next one, our absolute values. So our absolute value graph of g of x equals the absolute value of x. This pattern here is your rate of change is still constant. It's still going to increase or decrease by the same number. It's just it changes. It does both increasing and decreasing, whereas our linear function did not. Linear was just purely increasing for our parent function, although we can have some that are purely decreasing. Either way, it was constant, always just one of them increasing or decreasing. So for our absolute value here, this is going to be a V-shaped graph. Now, at any point in time, if you do want to type it in your calculator to get your table to graph it, you can. I clearly have these graphs memorized because I've been doing these for a few years, but you can always use that graphing calculator to help you if you need it. That's why it's there. So our absolute values, as I said, so we have a decreasing and we have an increasing, but the actual rate of change is constant. It's still going by 1. So this is going down 1 over 1, down 1 over 1, down 1 over 1. So it would be negative, but that's just telling us a direction. Here is up 1 over 1, up 1 over 1, up 1 over 1. It's positive, but it's still 1. It's still changing by 1. That part isn't changing at all, just the direction that it's heading in. So it's still constant like our linear, but it includes both directions, increasing and decreasing with it. So our domain is everything. Pretty much all of only our special cases is where it's not going to be everything. And this range is going to be greater than or equal to 0. It's never going to be lower than 0. It's always going to be greater than or equal to 0. And that's going to be true with your absolute values. They're always going to be greater than or equal to something. Or if it's negative and you flip it, it'd be less than or equal to. X-intercept, Y-intercept for the parent function is also still 0. Maximum number of roots or zeros. Because this graph turns and goes back up, you could have at most 2 roots. Because if I took this and I shifted it down, I could get it crossing at 2 different spots on the x-axis. So with our absolute value graphs, you could get at most 2 roots for that. And then our end behaviors, both of them are pointing up. So both my right side and my left side are going to be going to positive infinity there. This is a continuous graph, and this parent function is an even symmetry. It is symmetrical over that y-axis there. So pattern is kind of similar to the linear, but as I said, it changes direction. So that's how we know it ends up being absolute value. All right, quadratic. Quadratic, h of x equals x squared. Again, you can use your table if you want to. From your calculator, I'm squaring these values in my head. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So that's how I get my shape there for that. So the pattern here, there's really no consistent pattern here because the amount we're changing by. So if I go from here to here, I went up 1 over 1. Whereas from here to here, I go up 3 over 1. So the amount I increased by increased. So from here to here, I went up 5 over 1. So again, it keeps changing. So our pattern is increasing or decreasing. Because here, this goes down 5 over 1, down 3 over 1, down 1 over 1. So it depends on which side you're on. So this one has both increasing and decreasing sections, and the amount that you are increasing or decreasing by also changes. So our domain is everything, and our range is greater than 0. So it's very similar to your absolute value here for your domain and range. It's just, again, you can tell the difference because this was a constant increase, decrease. The amount we increased, decreased by here changed. So that's our differences between those. Our x-intercept, y-intercept here is 0. For the function family, a quadratic can have at most 2 roots. And behaviors are both going positive, so very similar again to the absolute value, so it's the rate of change that you have to look at for those to be able to tell the difference, because again, your characteristics look the same, so you have to look at the pattern. How is it changing? That's how you're going to actually be able to get the difference between them. All right. Let's go to these next 3. These next 3 are a little different. You haven't done too much with these ones at this point in time. So our cubic, we'll go with j of x equals x cubed. So our pattern for this is very similar to your absolute value. It's always either increasing or always decreasing, but so it's either increasing or decreasing. It's never both at the same time. It's one or the other. So cubing everything in my head to make my table here. And there's our graph. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, negative 2 cubed is negative 8. So it looks like you're linear kind of, but it does have a little bit of a squiggle to it because it's not a constant increase. So because it looks very similar to our linear, domain and range are both going to be everything. X-intercept, y-intercept are 0. This one is going to have at most one maximum because, again, it's not going to change the shape of the pattern. It's always going to follow that pattern there. So our end behaviors, right side goes up, left side is going down. This is continuous and it is odd. Because if you look at that table again, negative 1 gives you a negative 1, positive 1 gives you a positive 1. Positive 2 gives you an 8, negative 2 gives you a negative 8. That's the definition of odd symmetry, is those values are going to be opposite there. So, looks similar to our linear, but it's different because the increase is not constant. So, square root function. This was one of our special cases, so I'm going to put a little star there. That's one of our special cases that we dealt with last unit. So our pattern here, again, it's either increasing or decreasing. It's never both. The only ones that have been both so far are your quadratics and your absolute values. So our square root look like this. So the square root of 0 is 0. The square root of 1 is 1. 2 is a decimal, so I didn't do it. 3 is a decimal, but the square root of 4 was 2. And then I went to 9 because that was my next perfect square. So the square root of 9 gave me 3. So that's how I got my graph there. Again, use that calculator. Our domain here is just going to be greater than or equal to 0. It's never going to go past that point right there. And then our range here is going to be greater than or equal to 0. So our x-intercept and our y-intercept are both 0 on this. We can have at most one root. End behavior on the right side is increasing. End behavior on the left side, there isn't one. We're not going to write it because there's no arrow. It's not going to keep going anywhere. So there's no end behavior for us to describe, because it's not going anywhere. You have to have an arrow in order to be able to have an end behavior there. This is continuous, and it's going to be neither. It's not even or odd symmetry. So we'll go with M, because L looks like a 1. Cube root. We have not done too much with our cube root function. This is actually the inverse, put a little note in there, inverse of the cubic. cube root is your inverse of your cubic function. So if we remember, inverse just means we switch our x and our y points. So it's going to have a similar pattern. It's either increasing or decreasing, never both. So our cube root is going to look like this. So it's just basically our cubic inverted. Again, switch those x and y points. So it's going to be similar. Our inverses have similar domains and ranges. Remember, you're just switching your x and y, so really you're switching your domain and range as well. So the range of the first one is the same as the range on the second one. Our x-intercept and y-intercepts are both going to be 0. We're going to have at most one root. And behaviors are going up on the right side, down on the left side. We are continuous. And this one is going to be odd symmetry. That is symmetric there through the origin. All right, last 3. Reciprocal function. Thank you. Okay. All right, so reciprocal function 1 over x. This was another one of our special cases because, again, with a fraction, denominator can't be 0. So if you recall, can't really see it too well. We have an asymptote right there along the y-axis. So that's our dotted line there. 1, 1, 5. This one you just kind of have to remember the shape of the graph. This one actually, if you recall, which it's okay if you don't, really has 2 asymptotes. It has a vertical asymptote at x equals 0. And this one has a horizontal asymptote at y equals 0. So 2 asymptotes here, a vertical one and a horizontal one, both at 0. X equals 0, y equals 0. So our domain is everything but 0. Our range is everything but 0 as well. They kind of mimic each other, remember, with our 3 special cases. There is no x-intercept or y-intercept. So don't put 0, because 0 is an actual value. It's going to be nothing. There is no x or y-intercept here. So then there's no roots, because remember, a root is your x-intercept. And if we don't have an x-intercept, we can't possibly have a root. So that's going to be nothing. So our end behaviors, if we follow this, the right side here is decreasing. However, it's approaching 0. It's getting close to that asymptote. So it's approaching 0 this time. It's not approaching infinity or a negative infinity. It's approaching this asymptote here, which is 0. The left side is doing the same thing. The left side is approaching 0, but is never going to actually reach or touch 0. This is discontinuous, but it is an odd function. It is reciprocal over that origin. So that is going to be an odd function there. All right, 2 more. Exponential. I'll go with A for exponential. All right, A equals 2 to the x. Our pattern here is that it's either increasing or decreasing. For all exponentials, they're either increasing or decreasing. So our exponential function does have an asymptote with it. I don't know if you remember that from Algebra 1. But it's this little curvy guy here. I've always called it a Fichat graph for no real reason other than for some reason when I'm drawing it, I just make that sound. And when I was getting observed one day, I just wanted to make the person observing me try to write the word Fichat. So I kept saying it because I thought it was funny. So here we have a horizontal asymptote at y equals 0. It's not a vertical one because it's not one of our special cases. The vertical asymptotes really only show up with those reciprocal functions. So it's a horizontal asymptote though, because it does have this value it approaches with exponents. They never ever actually equal a 0. And we'll talk a little bit more about that when we get to our exponential unit. So our domain is everything because it's not one of our special cases, and our range is going to be greater than 0 because we have that asymptote there. It's not going to actually reach 0. No x-intercept because it doesn't touch the x-axis. The y-intercept is at 1. Now we could have an x-intercept if when I take this graph and if I shift it down, yes, we would have an x-intercept for that. But in our parent function, we do not. So, I mean, any member of the function family could have one x-intercept. End behaviors, right side's going up to infinity. Left side is approaching 0 because that's where our asymptote is. Remember, it always approaches the asymptote. This is continuous, and this is a neither function. This is neither even or odd. And then our last one, logarithmic graph. We will talk about this more later as well. B of x equals log base 2 of x. Your logarithmic, I just totally butchered that. Logarithmic is your inverse of your exponential. Logarithmic is the inverse of the exponential. So because it's the inverse of the exponential, this one has a vertical asymptote, whereas our exponential did not. Our exponential had the horizontal. So here we have a vertical asymptote at x equals 0, because again, we're switching the x and the y for those inverses. So this had a horizontal at y equals 0, therefore this one, when I flip it, becomes x equals 0. So then I'm just flipping my points from my exponential graph to get me there. All right, there we go. You can see both. So my range here was y is greater than 0. Because this is my inverse, when I flip it, my domain is greater than 0. So range was greater than 0, flip my inverse, so I flip my x and y, my domain is now greater than 0. My range was everything. I'm sorry, my domain was everything, so my range is everything. With your inverses, those flip-flop. That's what happens. So one x-intercept, no y-intercept. Well, come on, pal. I shouldn't put 0. No y-intercept, so nothing there for your y-intercept. And then we could have at most one x-intercept here. End behavior. So right side is approaching infinity still. This side is still slowly increasing, slowly going up. It's going to continue that pattern and it's going to keep slowly increasing. The left side is approaching 0 yet again. I'm sorry. The left side is approaching negative infinity because the left side is going to keep going down. We're going to keep going down, 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 down. Domain-wise, it's approaching 0. So that's why I misspoke. This value, though, is going to keep going down, so it is approaching negative infinity. It's continuous. It's neither even nor odd. So go fill in that one column, that second column there in that worksheet I gave you, and I will see you next class.